Hello, whoever has decided to tune in to my little channel. If you haven't noticed already, my channel name is Cult of Pythagoras because I have this habit of choosing really pretentious names and liking them for a couple minutes, and then once I kind of wear off the novelty of it, I think they're silly and ostentatious and all that. So I've I've chosen that name, but I've just kind of started referring to my channel as Cult of Pythagoras as COP, just kind of mentally. Um, so I wanted to make a little informal lecture series on measure theoretic probability, so probability at the graduate level. I am myself am currently a graduate student studying probability, and I decided to make this for a number of reasons. First of all, it was an idea I had in the back of my mind for a while, and then recently I'm making this during the coronavirus outbreak, so everybody's sequestered at home, and I have nothing better to do. I'm teaching I'm teaching classes by making YouTube videos. My lecture videos are going up for my Calc 2 course. So I was already making videos, so I figured I'd make some videos for fun as well. And I'm also studying for my candidacy exam, so this has the dual purpose of trying to be a service to the community and as just a learning tool for myself, more selfish than altruistic. But here we are. I'm making this probability series. So first of all, some prerequisites. As I said, this is at the graduate level, so what are you expected to know for this? Definitely real analysis. So at the graduate level, probability is completely in the language of real analysis, so we have to have real analysis. And just a short list of topics we definitely need. This is by no means comprehensive, but we definitely need to know about sigma algebras, which will be apparent by the end of this video, measure spaces, measurable functions, abstract integration, signed measure, the Radon-Nikodym derivatives. Not too much on signed measures, but at least to the point where we can form Radon-Nikodym derivatives. If your background in these areas is lacking, there's definitely a lot of excellent sources out there. So my go-to sources for real analysis would be Folland. He has an excellent book that's considered a classic, as is Rudin. I forget the colloquial name for Rudin's real and complex analysis book. I think it's Big Rudin or Papa Rudin. I'm not sure if that's real and complex or his functional analysis book, but either way, it's a classic. I don't really like Rudin, to be honest. Maybe I'll draw a lot of flack for that. I much prefer Folland. And then recently I saw this book by Zemer, which my university is now using for real analysis. And I didn't take that course I didn't take that course at all, but my friends who were taking it were using this textbook, and it seems very good. It's more modern style, so if you prefer that to something from the 70s or whenever Folland or Rudin are from, maybe Zemer's more your style. As far as sources for probability go, I think the pickings are a bit more slim. I have a lot of sources on my computer that I use and some actual hard copies. I had the privilege or maybe just luck of taking this course with, I think, a great professor. And he wrote his own lecture notes that didn't seem to follow the format of any books that I saw. So one of the common books is this book by Durrett, and we used it in our class as a kind of companion piece, but as we were looking at it and using it, I think it's got a lot of great exercises, but as we were using it, I realized I just really didn't like the structure of the book. I think the The order of subjects is kind of all mixed up. So I never really liked Duret. Again, I think a lot of people do, and I'm sure it's excellent for those in the right mind space. I think once I'm introduced to a subject a certain way, I kind of stubbornly stick to it that way. So I learned this material in a different order, and so I kind of prefer that order. So I think the way I learned it, I much prefer this book by Atherea, which is, I think, a Springer text, graduate text in statistics, but it's completely mathematical in its nature. It's if you're a mathematician and you don't want to associate with the lowly statisticians or whatever bias you might have, it's written in a completely mathematical style. If there's even a difference, I'll let you debate that. But it's great. It starts out with, again, this would be maybe another source for real analysis. It starts out with measure theory, abstract integration, all that kind of real analysis prerequisites, and then moves on to probability by chapter 6. So I'm kind of starting this lecture series at chapter 6 in Atherea, and I'll use it as a loose guide for the material. Maybe I'll depart from that in some circumstances. But loosely, the structure of Atherea from chapter 6 onward. And if you have any suggestions on probability books, feel free to let me know. With that in mind, I'll go ahead and start the probability material. So the first thing we need to do is define a probability space. So these came about, this formalism in probability really came about in 1933, thanks in large part due to Kolmogorov. I hope I'm not butchering that name. And it came about in this time of really a revolution, I guess, in the formalism mathematics, and math history is not my strong suit, but I would, in my naive way, say that this is during the time of Bertrand Russell and Lebesgue and other people kind of revolutionizing the logical underpinnings of mathematics, and a lot of developments in set theory and integration and analysis, things like that. So it's coming from that sort of time. So Kolmogorov made his own contributions in probability, to name one subject, but our axioms of probability are going to be due to him in their modern form. So let's lay some groundwork first. Let's consider an experiment, and I use that term loosely and abstractly. Don't picture somebody in a lab pouring liquids back and forth between test tubes. Just think of it as an abstract mathematical object. An experiment that is going to have something we call outcomes. So we group all these outcomes into a set omega. So this omega is our set of outcomes. And then we can consider subsets of omega as well, and we call these subsets of omega events. And we can group all these events together into a collection of subsets that we denote by script F. And maybe not all subsets of omega are in this event space, and that's a topic we need to discuss. But for now, let's think of script F as our subsets of omega, so our events. And a question, before we even think about questions, let's just see an example. So, for example, let's say I'm rolling a die 3 times and recording the face value of the die. Okay, so our omega, our set of our all possible outcomes, would be just all the possible face values of 3 rolls of a die. So maybe I roll my die 3 times, it's a 1 every time. I have the outcome 1, 1, 1. And then maybe it's 1, 1, 2, and so on. So my omega is just all the possible outcomes of my die rolls. Okay, all the way from 1, 1, 1 to 6, 6, 6. metal. And then we could consider a specific event, right? Let's say A is the event that all rolls result in even face value. So we could say that A is this set 222, 224, 226, maybe then 422, and so on. And I've just written it in kind of a neat order ranging from 222 to 666, but this order is not important, just the elements of the set. So that's one possible event, and this this A is in our set. Maybe it's in our set F, maybe it's not. But our elements of F would be sets like this. Okay, so maybe there's some rule that kind of governs what our set looks like for example, the set of all outcomes where the face of the die is presenting an even number. Maybe there's no logical connection between these individual outcomes in the event. So what properties would we expect of omega and F? And this is where Kolmogorov's axioms come in. Okay. And these are paraphrased. I've looked briefly at Kolmogorov's original paper, 1933. These are logically equivalent to what he wrote down, maybe, again, written in a bit more modern style, but they're the same thing. So first we have, if A is in the event space F, then its complement is in F as well. And maybe now is a good time to talk about kind of our intuition about F, our script F, our set of events. I consider all F to be all the events that we can give some sort of evaluation to. So in probability, we're mostly concerned with assigning probabilities to events. But maybe before we even get to that, maybe we could think of it as all the sets that we can determine have all the events that we can determine have occurred. Okay, so if I say A is in script F, then A complement is in script F. Meaning, if I can tell A has happened, then logically I can also tell if it hasn't happened, right? It's got to have this kind of binary nature. There can't be any gray area. If there's some gray area about whether A has occurred or not, then I can't really tell whether A has occurred. So if A is in script F, then A complement is in script F. All right, now number 2, the second axiom, if A1 and A2 are in F, then their union is also in F. And again, this meets with our intuition that if I know whether let's go back to our previous example, if I can tell whether the die has rolled up as a 2 or as a 4, then I can easily tell whether it was 2 or 4, right? Third, now we're getting to how we actually define our probabilities. In the third axiom, we state that there exists a non-negative set function P such that for any set, this is any set A in our script F, P of A is in between 0 and 1, and that P of omega is equal to 1. Okay, so we can call P our probability. We haven't shown it's a measure yet, but let's kind of loosely call it a measure for now. So our P, our probability measure that we're assigning to all events, is between 0 and 1. And we can talk more about the meanings of probability 0, probability 1 later. But all our probabilities are between 0 and 1. Okay, axiom 4. If A1 and A2 are in F, and their intersection is the empty set, then the union of A1 and A2, the probability of their union, is equal to their individual probabilities, PA1 plus PA2. And again, this is very logical. If we have two events that have absolutely no overlap, we don't expect their probabilities to have any kind of interaction. We expect their cumulative probability to just be the sum of their individual probabilities. Now note at this point, axiom 4 is just for 2 events, and we can extend that easily to a finite number of events, but we don't yet have a countably infinite number of events. Axiom 5, if an is in script f and an is subset of an plus 1 for all n, then the union of our an is in f, and the probability of our union is equal to the limit of pan as n goes to infinity. Okay, so we've stated the axioms, Kolmogorov's axioms. So let's look at the implications of these axioms. So if I didn't state it already, we're assuming from the outset that omega is a non-empty set. So that's not even really a consequence of these axioms. Let's just state that for absolute clarity. First consequence of these axioms is that our script f is actually a sigma algebra on omega. So what is this? Recall what a sigma algebra is. This is where some of that real analysis comes in. So what do we have for a sigma algebra? First of all, we need omega is in script f. And this is by our axiom that states our script f is closed under complements, right? If a is in f, that implies automatically that a complement is in f. And if a is a subset of omega, then omega is going to equal a union a complement. And since our script f is closed under complements, we see that omega, or excuse me, closed under unions, finite unions, we have omega is in script f. What else do I need for sigma algebra? I need, let's see, I need f to be closed under complements. Well, it already is, right? We've already assumed from our axioms that if a is in f, a complement's in f. Okay, and what else do we need for script f to be a sigma algebra? We need f to be closed under countable unions, meaning if a1, a2, and so on are all in f, then we need the countable union of an to be in f. Well, this is a result of our fifth axiom. Let's say the fifth axiom doesn't state it directly, but let's call bk the union of the first k sets an. Okay. Well, we see bk is a subset of bk plus 1, clearly. And actually, we have the infinite union of bk. That should be the same as the infinite union of my an, right? You can check this on your own. From axiom 5, since b satisfies these conditions, we have union, we have immediately from that axiom that the union, the infinite union of bk's is in f. Well, this is just equal to the infinite union, countable union of my an's. Okay. So we see that our countable union of sets is also in script f. So our script f meets all these three conditions to be a sigma algebra, so it's a sigma algebra. Okay. Going back to where we were, okay, we were here, so, all right, omega is a non-empty set, script f is a sigma algebra on omega, then it follows that omega f is a measurable space, right? A measurable space is just a set combined with a sigma algebra on that set. Okay. And then the next conclusion we could draw is that p is a measure, a finite measure, on that measurable space. Okay, so we need to show p is a measure. So what do we need to show a set function as a measure? Well, we need, let's see, we need p to be a non-negative set function. We have that by assumption, right? That's in our axioms. What else do we need? We need p of the empty set is equal to 0. Well, do we have that? Yeah, that we have that from the axiom that states that p of omega is equal to 1, right? We have this by assumption. Well, omega is equal to omega union the empty set. And these two sets are disjoint, right? Omega and empty set is equal to the empty set. So by our axioms, we have, well, the probability of this is equal to the probability of these two individuals. And then on the other hand, we have omega union empty set is just p of omega. So p of omega is 1. And then on this side, I have 1 plus p of the empty set. And since p is non-negative, it must be that p of the empty set is equal to 0. Okay, so condition 2 is satisfied. And what's the third condition we need for a measure? We need countable additivity, right? We need if a1, a2, and so on are disjoint, then the measure of the union equals the sum of the measures. Okay. Well, let's see. First of all, let's again consider the finite union of ANs. Let's see. AN n equals 1. We could again consider the first k, the union of the first k elements. Well, this is going to be a subset. I'll use the same technique I used previously when I said, okay, bk is equal to that. But we can skip the bk. All right. This union from 1 to k is going to be a subset of, excuse me, of that, right? And by axiom 5, we know that means, let's see, by axiom 5, we know this infinite union is in script f, and it's going to be the limit as k goes to infinity of this. Well, by one of our axioms, let's see, we said, okay, these are all disjoint. We had it for just a pair of disjoint sets, but it's trivial to extend this for any finite number of sets. This p of this finite union from 1 to k is the sum of the individual probabilities. Okay. And then just by the definition of what an infinite sum is, what is this? That is this. Okay, so we have this is equal to this, which is the definition of countable additivity. So our set function is countably additive. And this sum might not be, let's see, I guess, well, it is always going to be finite, right? Because, well, yeah, they're disjoint and they're all subsets of a set of measure 1. So this sum will be convergent for disjoint sets. And it has a sum of at most 1. So we have our three conditions. We have countably additive. We have the measure of the empty set is 0. And we have, well, by definition, P is a non-negative set function. So P is in fact a measure, and we call it the probability measure. Okay. And in general, when, excuse me. So in general, when we have a set of finite measure, when we have a finite measure space of measure 1, we call it a probability space. That's just the definition of what a probability space is. So in short, omega f and p combine to form a finite measure space. That finite measure is 1, and we give that thing a special name. It's a probability space. So again, omega is our sample space, f is our event space, and p is our probability measure. Now, maybe now is a good time to talk about f a little bit. Previously, I said, okay, just consider f to be all our subsets of omega. But once we think about this in the language of real analysis, we know that f might not consist of all subsets of omega, right? We in real analysis, when we make a sigma algebra on a set, we have to differentiate between the measurable sets and the non-measurable sets. So script f is actually going to be the collection of measurable subsets of omega. So it's not necessarily all subsets of omega, but it's going to be the measurable subsets of omega. And how do we define measurable? Well, there's different ways to do that. If we just put a sigma algebra on our omega, then all the sets in our sigma algebra are measurable sets. If, for instance, we define a Lebesgue measure on a space, well, then the measurable sets are going to satisfy that Lebesgue outer measure property. So there's a bit of subtlety on what sets are included in here. So that would be definitely a real analysis topic that hopefully you're comfortable with. Just a quick note before we talk more about the real analysis aspects of probability. The elements of the sample space big omega are called sample points, also known as simple events or elementary events, and they're denoted as little omega. Okay, so that's not a W, that's a little omega. So maybe you're asking why do we need this structure of a probability space? Why do we need this these sigma algebras and so on? What do we gain from it, or why is it necessary? Well, obviously we want to be able to assign probabilities to events, and maybe it's clear to you if you've studied measure theory that that's looking like it's going to be a measure. So what's the deal with that? Why do we need it? Well, we need to be able to deal with infinite collections of events. Maybe if everything's finite, we could consider it in a more naive way. But when we start dealing with infinite collections of events, this measure theory stuff starts to be really important. And the key premise here, as I stated a minute ago, is that we might not be able to measure all subsets of omega. If you've studied real analysis, we know that I've actually made a video on, there's a video of this on the channel, why we need measure theory. If we admit the axiom of choice, it can lead to some very paradoxical results, like the Banach-Tarski paradox, where we can decompose a sphere into some pieces and rearrange them and get two identical copies of our original sphere, which just totally throws our intuition out the window. But what that tells us is that we have non-measurable sets that we can't really assign a meaningful number to, or probability in this case. So we really need to confine ourselves to a sigma algebra of events. Okay, when we do that, everything should work out nicely. Our system should be consistent and lead to logical results. So just to state that briefly, we need sigma algebras. We gain some stuff from this real analysis framework as well. We get all the language of real analysis. We get all the techniques from real analysis. So a lot of probability you could consider as just analysis on a set of measure one. It's almost entirely analysis. There are some properties and definitions and so on unique to probability, and there's actually quite a lot, but it's all starting from this real analysis framework. So all probability is written in the language of real analysis. So just some examples of that are random variables that maybe you're familiar with from previous courses on probability. These are just going to be measurable functions from our probability space into some other measurable space. And then expectations, our expected values. These are just integrals on our probability space. So we need abstract integration. And then from our real analysis, from our abstract integration, our Lebesgue integration, we get these powerful convergence results, the monotone convergence theorem, the Lebesgue-dominated convergence theorem, Fatot's lemma, etc. And we can use these on our abstract measure spaces, our abstract probability spaces. So they don't necessarily have to be on the real line. They don't. They can just be on sets. We don't even need metric space structure. I don't. Let's see. Do we even need? Do we need topology? Do we need a Borel sigma algebra? I don't think so. I think we can just have. Abstract set. So just some abstract set omega. We will have additional structure unique to probability, as I said. The idea of independence, correlation. These are things unique to probability that add a little more unique structure to the field, not just strictly real analysis. So before we move on to the consequences of these axioms, let's talk a little bit more about this probability space structure. So our script f may be finite or infinite. It really depends on what our omega is. If omega is, let's see, if I suppose, let's see, could we have a finite sigma algebra on a set of with infinitely many elements omega? Possibly. Let's see, I guess the simplest sigma algebra would just be the trivial sigma algebra, the empty set, and omega itself. So yeah, we could have a finite sigma algebra. But let's see, if we couldn't have countable sigma algebras, let's see, if we've studied some real analysis, maybe we know the only two possibilities are our sigma algebras either got a finite number of elements or an uncountable number of elements, so there's no countable sigma algebras. But our sigma algebra may be finite or it might be infinite. If omega's finite, then our sigma algebra is definitely finite, right? Because all sigma algebras are subsets of the power set. So if omega is finite, then the power set of omega is finite, and so script f necessarily has to be finite. We could have omega be something really unintuitive, I guess. Maybe an example would be the omega is the set of all continuous functions. So our sample points are just continuous functions in that space, and this would be a topic leading into Brownian motion. That's way down the line for me to present on. I need to learn it a bit better myself before I talk about that. But these sets omega can be anything from just these finite sets representing our dice rolls to continuous functions. They could be they can span a wide range of objects, from very simple to very complicated. Things we should definitely know from real analysis dealing with measure theory and so on. We got to know the sigma algebra basics. So, for example, you should know that the intersection of sigma algebras is sigma algebra, and that's an arbitrary intersection, whether it be finite or countable or uncountable. We should know what a generated sigma algebra is. The smallest, if we have a collection of subsets of omega, which we denote, how would we say this? Epsilon, I guess. Sigma epsilon would be the smallest sigma algebra containing that collection epsilon, and other basics like that. The product sigma algebras, things like that, and maybe some special mentions. Things that deserve special mentions are Borel sigma algebras. So once we have a topology, we get this additional structure, I guess, of Borel sigma algebras. So the sigma algebras generated by the topology. So again, we can consider sigma algebras on just abstract sets or topological spaces, metric spaces, vector spaces, and so on. So Borel sigma algebra, I guess, would be the kind of first level of additional structure we have other than just a sigma algebra on an abstract set. So with Borel sigma algebras, we can talk about things like continuous functions. That's really the great thing about Borel sigma algebras. We get the structure of continuity from a topological point of view. And of course, we should know about complete measure spaces, complete probability spaces. These are measure spaces where every subset of a null set is also a null set and is also measurable. Okay. Something that's not usually covered, I suppose, in real analysis course is this pi lambda theorem, which will come up in probability theory quite a bit. So first, some background on, let's see, the pi lambda theorem, I should also mention, is also called, I think the Doob-Dinkin theorem is also another name for it. These pi system lambda systems are also called like Doob systems and Dinkin systems, I think. I'm more familiar with the pi lambda terminology. So a pi system on a set X is a collection P of subsets of X such that the collection is not empty, and if A and B are in P, then their intersection is in P as well. So closed under finite intersections. A lambda system, on the other hand, is on X is a collection L of subsets of X such that X is an L. If A and B are an L and A is a subset of B, then the set difference B minus A is an L. And I've seen number 2 stated as being closed under complements. They're logically equivalent. If A is an L, okay. Let's say A is an L. We know omega is an L, and we have condition 2. Then omega minus A is an L, and this is equal to a complement. Okay. And it goes the other way as well. Condition 3, let's see if we have countable disjoint sets in L, and AN is a subset of AN plus 1 for all N, then their union is an L. All right, so this is background. The pi lambda theorem states if, I'll call it epsilon. I don't know if this is supposed to be an epsilon or a script E or what. This is how it's usually written, so I just kind of write it this way without thought to how to pronounce it. Let's call it epsilon for now. If epsilon is a pi system and L is a lambda system with epsilon subset of L, then sigma epsilon is a subset of L, meaning, okay, the sigma algebra generated by epsilon is an L. Okay, so this is just a proof sketch. We, similar to generated sigma algebras, we can talk about the smallest lambda system containing a set A or a collection of subsets A. So define this lowercase this L of A as the smallest lambda system containing A. Then note that if B is both a pi system and a lambda system, then B is a sigma algebra. If C is a pi system, then L of C is also a pi system. Okay, so these are the three lemmas or results that'll kind of help us in our proof. So now consider our collection of subsets epsilon by, let's see, 1 and 3. L epsilon is a lambda system and a pi system. So if we consider that lambda system, that smallest lambda system containing E, well, that lambda system has to be a subset of L, since E is an epsilon is an L. And by 2, L of epsilon is a sigma algebra, since, let's see, L of E is a lambda system and a pi system. So L of epsilon is a sigma algebra containing epsilon. And by definition of the generated sigma algebra, we have the generated sigma algebra is a subset of L of epsilon is a subset of L. Okay, so why is, you might ask, okay, why is sigma epsilon a subset of L epsilon? Well, let's see, this is a sigma algebra containing epsilon, so, and this is the smallest sigma algebra containing epsilon. So it has to be that sigma of epsilon is a subset of L of epsilon. And since this is the smallest lambda system containing epsilon, L of epsilon has to be a subset of big L. Okay, so that's our little proof sketch. So now we should talk about the results, the implications of our axioms. This has all been kind of the structure of our probability space. So our probability space tells us, our axioms tell us we are dealing with a measure space. So most of this has been talking about the structure of the measure space and the sigma algebra script F. But now let's just see some simple results of our axioms. Okay, so maybe one of the first elementary properties we should talk about is the probability that A complement equals 1 minus probability of A, for A in our sigma algebra F. Now this, this we could derive directly from the axioms of probability, from Kolmogorov's axioms, or we could think of this in terms of a real analysis setting of a measure space. So we have finite additivity in a measure space. So if this follows directly from finite additivity, we in normal real analysis situations, we have to be careful because we're usually working with the extended real number system. So the way this would, let's see, work is from a real analysis setting, or or approaching from the axioms, we would have that the probability of omega, which is equal to 1, is equal to the probability of A plus probability of A complement, because these two are disjoint. And then what we do is we just subtract probability of A from both sides. And we have our result. And this is, again, just we could view it as either coming directly from the axioms or just from the fact that our probability space is in fact a measure space which has finite additivity. And this subtraction is no problem because these are both, everything's finite here. This is a finite number and this is a finite number. If we had a possibly infinite a measure space where the let's see, non-finite measure space, infinite measure space, we would have to be careful of the subtraction and check that A is a set of finite measure, because the subtraction infinity minus infinity wouldn't be defined, right? So that's not an issue on probability spaces because everything's finite measure. So this is one of the nice aspects of probability spaces. Everything's finite, so I don't have to worry about this subtraction being defined. It just is. Okay, so again, we have probability of A complement equals 1 minus probability of A. Very important result. Then we have if A and B are in our sigma algebra F, and A is a subset of B, then probability of A is less than or equal to probability of B. So again, this could be derived directly from the axioms or from the monotonicity of measure, right? So let's see, we could have B is equal to A union B minus A, right? The set difference B minus A. And what is B minus A? Well, that is just B and A complement. Let's see, B is an F, okay, that's an F. This is an F by assumption. And then let's see, since B and A are an F, let's see, A complement's an F because A is an F. And then a sigma algebra is closed under intersections. So this is an F, okay? So then this is an F. And then A and B and A complement, B intersection A complement, those are disjoint sets. So probability of B is equal to probability of A plus probability of B and A complement. And this is greater than or equal to 0. So we have probability of B is greater than or equal to probability of A. So very straightforward. And that about wraps up. These are the two clearest results of our axioms, and there are many others that follow. Most of them are pretty basic, and you would see more explicitly in maybe an undergrad course. For example, I took these two just directly from Sheldon Ross's first course in probability undergrad textbook, but they're worth restating here. If you are comfortable with measure theory, a lot of in real analysis, a lot of these results will come directly from there and should already be familiar, and we'll address them more explicitly as they become relevant. As far as solving results, solving problems for this section, I don't have any at hand right now. Hopefully, I would actually like to make a kind of blog where I keep some problem sets and things like that and answers and solutions as a kind of companion to this. I don't have anything up right now, and I can't think of any problems for this probability space material off the top of my head. Once we start talking about random variables and things like that, the problems will be much more readily available. So we'll start solving some actual problems in the next installments. I hope you enjoyed the video, and obviously I have a long way to come, long way to go in terms of being comfortable in these presentations. I know I have a lot of vocal tics like ums and and so ons, things like that. So I'll try and work on that, and I'll see you next time.